we are going to start our review of projectiles fired at an angle, the vectors for them, by reviewing sine and cosine for a right triangle. So I have my right angle, I have my reference angle. The side that is touching that angle is called side adjacent. The side that is opposite of that angle is side opposite. And the longest side of the triangle is the hypotenuse. Now sine theta, get sine theta, there we go. Sine theta is the ratio of side opposite divided by the hypotenuse. Oh, back up. Cosine theta is side adjacent divided by the hypotenuse. Now if I take the sine theta equation and I multiply both sides by hypotenuse, I get hypotenuse times sine theta equals side opposite. And if I take the cosine equation and multiply both sides by hypotenuse, I get hypotenuse times cosine theta equals side adjacent. On the next slide, I'm going to do this with some numbers. So I need a right triangle again. Alright, here's my angle, my right angle. My angle for this is going to be 35 degrees. And my hypotenuse is going to be 100. So using the equation from the other side, hypotenuse times sine theta equals side opposite. So the hypotenuse is going to be 100 times the sine of 35 degrees, which will give me 57.36, and then hypotenuse times cosine theta is side adjacent, so that will be 100 times the cosine of 35 degrees equals 81.92. Now I'm going to apply this to projectile. So I have the ground, it's horizontal. Projectile is fired at 28 degrees above the horizontal, and its initial velocity will be, if I can get my pen to work, there we go, 50 meters per second. Now looking at this, remember, whenever you fire a projectile, its launching point is the origin of an XY coordinate system. So I have that initial velocity that is fired with. It has, along the x-axis, a projection or a component part in the x direction. And that's part of the velocity that takes it across the ground. And there's a projection or a component on the y-axis, and that's going to be the velocity initial in the y, and that should be initial in the x. And of course, as you know, the velocity in the x direction does not change. So if I turn this into a triangle, I have the velocity in the x going that way, I have the velocity in the y going that way, and I have the direction of its initial velocity. So that's 28 degrees, and it's fired at 50 meters per second. Now I'm going to rewrite the equations the way I had them in class. My velocity initial in the y is going to be my velocity initial as a whole, which is the hypotenuse, times the sine of the initial angle. So velocity initial in the y will be 50 meters per second times the sine of 28 degrees. So velocity initial in the y is going to be 23.47 meters per second. Now, my velocity initial in the x is going to be velocity initial times cosine the initial angle. So velocity initial in the x will be 50 meters per second times cosine of 28 degrees. I'll fit this in. So velocity initial in the x will be 44.15 meters per second. Okay, so next, let's do this one more time, actually a couple more times. Let's do another one. So I'm going to draw a right triangle again. That's my velocity in the x, my velocity in the y, and the velocity as a whole. So let's fire at 30 degrees. My velocity initial will be 20 meters per second. So on this side is my velocity initial in the x, and on this side is my velocity initial in the y. Alright, let's find the component parts of this initial velocity. The velocity initial in the y is velocity initial sine theta initial. So velocity initial in the y will be 20 meters per second times the sine of 30 degrees. Sine of 30 degrees is 1/2, so my initial velocity in the y direction is 10 meters per second. Now, my velocity initial in the x will be velocity initial cosine theta initial. So my velocity initial in the x will be 20 meters per second times the cosine of 30 degrees, which gives me a velocity initial in the x of 17.32 meters per second. We'll do one more. I'm going to choose a different background. Let's use graph. Okay, so again, whenever you fire a projectile, you take that original spot where you fire it from. Oh, let me back up. Let me do a straight line. Wherever you fire it from, you treat that as the origin of an XY coordinate system. So I have my velocity initial as a whole. He has a projection or a component along the x-axis, and he has a piece along the y-axis. Sorry, program shut off, so I'm not sure where I ended up at, but this thing has a velocity initial equal to 45 meters per second, and it's being fired at 60 degrees above the horizontal. I know it looks a little shallow for 60 degrees. So this part is my velocity initial in the x, and this part is my velocity initial in the y. And I don't have to slide the y vector over and make the triangle. I can just look at it like this. So my velocity initial in the y direction will be, there we go, velocity initial sine theta initial. Velocity initial in the y, then, there we go, is 45 meters per second times the sine of 60 degrees. So my velocity initial in the y is going to be 38.97 meters per second. My my velocity initial in the x will be velocity initial cosine theta initial. So velocity initial in the x, oh, should be an equal sign there, will be 45 meters per second times the cosine of 60 degrees, and the cosine of 60 degrees is 1/2, so my velocity initial in the x will be 22.5 meters per second. And let me erase these things down here where they came from. Alright, so that concludes our review of vectors for projectiles fired at an angle.